Hi, this is a recording of me using COMSOL Multiphysics to simulate a solid mechanics problem, in this case a bone with a little fracture in it. We'll see how that affects the distribution of stresses and things within the bone. And so this is one of a couple videos that I'm putting up on YouTube to help you out in Bioengineering 10. If you're interested in doing a fluid flow simulation, then you can see that in the other video. Alright, so the first thing we'll do is launch the VPN for the College of Engineering. Of course, this all assumes that you've already installed the VPN for the College of Engineering as well as installed COMSOL Multiphysics to your computer. If you've done all that, then you should be able to find the Cisco AnyConnect client on your computer and fill that in there and hit connect, and then we're going to log in with your College of Engineering credentials. This isn't your usual NetID login. This is the one that's specific to the College of Engineering. So now I know I'm connected because I see this little padlock icon up here. Okay, now we're ready to run COMSOL, and so that lives on my computer under here, and it takes a moment to launch. So we will sit back and wait. Okay, there we go. So we'll always start with the model wizard here, and I've always suggested that people start with a 2D simulation instead of a 3D because the 2D is a lot computationally easier and more likely to succeed. Now, everything I've been playing with is up here. In this video, we're going to go after a solid mechanics simulation. I can see it here in my recently used list, or if you can't find it up there, you can find it under structural mechanics and solid mechanics parentheses solid. There it is there. So I'm going to click add after selecting that. We'll see it appear down here in my added physics interfaces. I click next to move on to the study. Now in solid mechanics you have a lot of these to choose from, but I'm going to choose one of the simple ones, which is a stationary study, which as it describes here is for variables that don't change over time, which is what we want to do with this. Alright, now I'm ready to click done, and in a moment we'll be rewarded with the blank screen here. So it's ready for me to start drawing my model. Now the first thing I always change here are the length units. It defaults to meters. I find that's not always the most useful unit for these sorts of problems. And so for a bone that we're going to simulate, I think maybe centimeters would be an okay substitute. So I'm going to change that to centimeters. We see that's updated here. And I like to zoom out so that I can see the full range over which I'm going to be drawing. So this is in the 10 to 15 centimeter range, which is a fine length for a little bone that we're interested in simulating, so I'm going to start with that. Okay, now I'm ready to draw it, and I like to first draw everything out of simple shapes like rectangles. So in this example, I'm going to draw my bone in a couple pieces here. This first piece here, and made out of a rectangle, and a second part here made out of another rectangle. You'll see why I'm drawing it in two pieces in a minute. I could have drawn just one rectangle, but that would have made it so I couldn't select certain boundaries here that I'm interested in working with later on. Okay, so there's my two rectangles. This represents a long, thin bone like your femur or something. And you see that COMSOL automatically puts this form union operator here, meaning that once we are ready to run this, COMSOL is going to put both of those together into one long, thin rectangle that simulates the bone. That's what we want. Okay, so we're done here with the geometry. I can move on down the list over here. So remember with COMSOL, we are generally guided by the order of operations over here on this little model builder list. And so the next thing that catches my eye is the materials. When I click on it, I see the error saying that domains 1 and 2 over here need a material assigned to them. So let's do that now. I'll right-click on Materials, and I have a couple options. I could add a material from the library. In this case, bone doesn't appear in the default COMSOL library, so instead I'm going to select Blank Material, and I'm going to add a custom material using values that I looked up for bone. So if you want to do this, just Googling the material that you're interested in simulating and then Young's modulus or Poisson's ratio or density, you can very easily find ballpark values for whatever material you're trying to simulate. Now it doesn't matter if it's exactly the same material. For example, in lecture I was simulating a blood vessel wall, but I used material properties from rubber. That's close enough, right, for the purposes that we're studying in this class. So we defined Young's modulus and Poisson's ratio in lecture, and so you know what those mean. And I've looked up values for them for bone. For Young's modulus, a value I found was 10 gigapascals, so that's 10, and then there's 10 kilopascals. 3 more zeros gets us 10 megapascals. 3 more zeros gets us 10 gigapascals, so a very large number. And then for Poisson's ratio for bone, I found a number in the literature of 0.3. And then for density of bone, that varies a lot by the type of bone we're talking about, but a good approximation is 3,050 kilograms per meter cubed for the density of bone. Okay, so that is my custom material. I can name it if I want. Here's the label for it. I'm going to call it bone if I like. And then the key thing here, I see the selector here is active, and that domains 1 and 2 are already here, and they're colored blue over here. So COMSOL's already done the work for me, and it has assigned my bone material to both of these domains. So that's great. Okay, what's next? Going down my list over here, I see the solid mechanics physics that we added, and it has a few default things to it. Let's look at the defaults here. The materials are all a linearly elastic material, and the Young's modulus and the Poisson's ratio and the density are all inherited from the material properties that we just set, so that's good, nothing to change there. The initial condition is that all of these boundaries are free, meaning they are free to move or have they have no constraints on them. They're free to move or do whatever the case may be. And the initial values of the material here is that they're not moving or under any sort of motion. So it's a long-winded way of saying that this piece of bone has no forces on it. So if I simulate it at this point and right-click on Study 1 and select Compute, I expect to see a boring result like that, showing the stresses inside of my piece of bone. You see over here on the color bar that number is 0. The color green corresponds to 0. So our piece of bone with no load on it, with no forces of any sort, it has no stresses in it. And that's not surprising, but I like to simulate it early on like this just to confirm that everything's working. So I know everything I've done up to this point is correct. Now what's left is to add something else interesting to it. And so we'll go back up here under solid mechanics, right click on that, and you can see all the different sorts of forces and loads and things we can apply to this piece of bone. So the first one that's probably most interesting for this sort of demonstration is a boundary load here. I select that. The boundary selection mode here is active, meaning it's waiting for me to select the boundaries on which I want this load to be applied. So let's apply it, say, here. So this represents applying a force to this surface of this bone. We'll see how it reacts to that. And then we need to define that force. It's down here. And you see you can define it. A force is a vector. It's in both the x and y dimensions. And so I want to apply it to the right. So in COMSOL's units or interfaces here, dimensions, that means a positive direction in the x direction. So let's put something there like 1 Newton per meter squared of force per unit area applied in that direction there. Okay, so now I've added one thing. Let's simulate it again and see what happens. And we get an error, and the reason that's not surprising, and you can try to read this and decide if you think you can understand that error, there's not much to gain from that, but I'll tell you what happened, right? We applied a force to this side of our bone, but we didn't have, if you will, an equal and opposite force or any other sort of force keeping the bone in the same place, right? And so as a result, this bone moved to the right in our simulation, and nothing ever stopped it from continuing to move to the right. So the simulation never found a fixed or a stationary or a steady state solution to it, and so it failed. So that's our hint to tell us that we need to add something that keeps some other part of this bone from moving, right? And so the easy thing for that might be to hold some part of the bottom of the bone here stationary. So let's go back up to solid mechanics, right click on it, and select a fixed constraint. And then it's up to me what side I want to have fixed. I could have perhaps select this bottom location here, and now in our simulation we're applying a load here while keeping this part of the bone stationary. And so that you can imagine is a realistic sort of load that some bone in your body might experience when you're walking around or whatever. Okay, so that's done. There's nothing to configure in that after selecting that domain has a fixed constraint on it. So I'm ready to go back to Study 1, right click on it and say Compute, and we'll see if this changes anything. And it did. So here we see the von Mises stress here, so just basically highlighting regions of this where the stress is localized. It's the highest down here because this is the part of our model that's being held stationary, and so all of the force that's being applied to this, it's like a gigantic lever that's kind of concentrating a lot of the stress that they're adding to this down here at the stationary part. So that's not too surprising. But from a physiological point of view, that means that if I really had this sort of situation in the human body, I would expect a breakage of the bone. If it were to occur, I would think it might occur down here where we see these reds, because that's the part of this bone that's being exerted to the highest, that is under the highest stress and most likely to fail. So let's do one more thing to our bone and try to add in a little defect, perhaps a breakage from a previous injury, and see how that affects the distribution of stresses inside our bone. So to do that, I go back up to my geometry entry shown here. And now I'm going to add something to this that simulates a break. And so I like to use a little circle here. It's going to thin out part of my model. I'll show you how I'm going to do that. So remember, in COMSOL, what you draw is the material you're simulating, right? And so I want to find a way to basically whittle out of my bone a void area that is going to be my break, if you will. So I'm going to do that in this case by drawing a circle onto it like that. I might move it down a little bit too. How about right there? That looks good. And so now I'm going to tell COMSOL to keep this part here, the two rectangles of the bone, but subtract out of that this circular region here. So I'll be left with a bone with a chunk taken out of it. Now to do that, we need to add a particular operator to this. I'll right-click on my geometry again and select Boolean difference. So the union adds two things together. That happens by default. The intersection would keep just the region of overlap that's common between two domains, but the difference is the one I'm interested in. That will take some parts and add them in, and then take other parts and subtract them out. Let me show you. So right now the selector for the objects to add here is active. That's my clue to say I need to click the domains that I want to keep in my bone. So that's this part and that part. Very good. Now I click this little toggle switch here to switch over to select the objects to subtract, and the parts I want to remove are this circle right there. Okay. Now if I click Build All Objects, you'll see what happens. Yeah, there's my bone, what's left, and you see that circular domain has been whittled out or carved out of the rest of my bone. And that's just right. So sometimes it's good to look back under the rest of your boundaries and make sure that nothing has changed. COMSOL is quite good at keeping keeping your initial boundary selections correct, even if you edit the geometry in between, but occasionally it messes up. So it's good to go down here and confirm what's going on. So we see the free boundaries there. It's basically every boundary except the one with the load on it and the one that's fixed. Here's the boundary with a load on it. That's correct. And here's the boundary that's fixed. Yeah, that's correct too. All right, so it looks like everything is still as it should be. So I right-click on Study 1 and select Compute, and we will update our simulation. Yeah, very nice. So you see a very different result now. If I zoom in on the bottom part of the bone here, you see that before our stresses were localized in this region down here, which was right, we said, at the very base of this long lever, and that was the point where the stresses were highest. But now, because we have injured this bone or somehow thinned it out, perhaps this is a model for osteoporosis or some other condition where someone has weaker or thinning regions within their bones. Because of that, we see the stresses now, these red colors are localized within this thin region here. So now in this case, if this were in a patient and they were experiencing this sort of force on this part of the bone that's shaped like this, I would expect a breakage to occur in this region, which maybe isn't surprising. But as I make more complex models, I could actually predict really interesting biomechanics and aspects of the human body by simulating these sorts of interactions in COMSOL. Okay, so that's that. So for Design Challenge 3, remember I want you to do something similar to this and simulate your own interesting bioengineering relevant system in COMSOL Multiphysics. It could be using solid mechanics like I just showed you, or it could be using fluid flow like I show you in the other YouTube video. And that's all I'll expect from you. Okay, thank you. Bye.